Picture this, a colossal burst of energy so powerful that it lights up the vast darkness of the cosmos, outshining entire galaxies in mere seconds. These are not the products of imagination or science fiction. They are very real phenomena etched into the fabric of our universe. From the explosive origins of existence itself to the violent deaths of stars and the dramatic collisions of celestial giants, space is a theater of unimaginable forces at play. Each explosion, a testament to the raw power of the cosmos, carries secrets that not only awe us but also hold the keys to unraveling the mysteries of how everything we know came to be. In this journey, we will uncover 30 of the most staggering cosmic detonations ever recorded, each one a step closer to understanding the brilliance and chaos of the universe we call home. Stay with us as we dive into the heart of creation and destruction, where the boundaries of our understanding are constantly pushed to the edge. Now turning to the very beginning, let us explore the ultimate explosion, the Big Bang, the event that gave birth to everything we know. Around 13.8 billion years ago, an unimaginable eruption of energy ignited the expansion of our universe. Before this event, there was no space, no time, not even the faintest whisper of matter. It all began as a singular, infinitely dense point, often referred to as a singularity. Then, in a fraction of a second, this singularity expanded rapidly, unleashing a colossal wave of energy that set the foundation for space and time itself. The Big Bang was not an explosion in the conventional sense, but rather an expansion, a stretching of space that continues to this very moment. The energy released during this event was beyond comprehension, creating the raw materials for galaxies, stars, and planets to form over billions of years. Scientists have studied the faint afterglow of this event, known as the cosmic microwave background radiation, to piece together its extraordinary story. This remnant energy tells us that the universe has been expanding and cooling ever since. The Big Bang not only marked the beginning of the universe, but also set the stage for the creation of elements, the organization of matter, and the vast cosmic structures that populate the universe today. As monumental as it was only the first of many awe-inspiring events in the cosmic timeline that remind us of the sheer power and wonders of existence. Moving forward, we unravel one of these extraordinary phenomena, the hypernova, where the death of a massive star creates a spectacle of energy on an almost incomprehensible scale. Moving forward, we delve into the spectacular phenomenon of hypernova, a cosmic event that stands among the most powerful in the universe. While supernova are already awe-inspiring explosions marking the death of a star, hypernova take this to an entirely new level. These titanic explosions occur when massive stars, far larger than our Sun, exhaust their nuclear fuel and collapse under their own gravity. Unlike a typical supernova, which might leave behind a neutron star, a hypernova often results in the formation of a black hole, a region of space where gravity is so intense that nothing, not even light, can escape. The energy released during a hypernova is staggering, sometimes hundreds of times greater than that of a regular supernova. To put it into perspective, a single hypernova can outshine entire galaxies filled with billions of stars, if only for a brief moment. In the process, hypernova also unleash powerful gamma-ray bursts, which are narrow beams of intense radiation that shoot out into space at nearly the speed of light. These gamma-ray bursts can travel billions of light years, briefly becoming the brightest objects in the universe and allowing astronomers on Earth to detect them from incredible distances. Such events not only signify the dramatic end of a massive star's life, but also play a crucial role in enriching the cosmos. Hypernova scatter heavy elements like gold and uranium into space, seeding future generations of stars and planets. They are a poignant reminder of how destruction and creation are intertwined in the cosmic dance of the universe. As we continue our journey, we turn our attention to a specific and remarkable supernova event, one that illuminated the night sky and gave astronomers an extraordinary opportunity to study the life cycle of stars up close. Now turning to one of the most extraordinary stellar events in modern history, we have supernova 1987A. Discovered in 1987, this supernova marked the closest observed explosion of its kind in over 4 centuries, occurring in the Large Magellanic Cloud, a neighboring galaxy a mere 170,000 light-years away. Its proximity gave astronomers an unprecedented opportunity to witness and study a star's explosive death up close. The progenitor star, known as Sanjalik-69302, was a massive blue supergiant, an unusual candidate for a supernova which only added to the intrigue. When it finally collapsed, the explosion unleashed a burst of energy so immense that it briefly outshone the entire galaxy. The light from supernova 1987A illuminated Earth's skies for months, visible even to the naked eye in the southern hemisphere. This event also marked the first time scientists detected neutrinos, nearly massless subatomic particles, emitted by a supernova, a groundbreaking discovery that confirmed key theories about how stars explode. Today, the remnants of supernova 1987A continue to captivate astronomers. A glowing ring of gas and dust surrounding the explosion site constantly evolves, offering a real-time look at the aftermath of such a cataclysmic event. This ongoing cosmic spectacle has become a natural laboratory for understanding not just the final moments of massive stars, but also the formation of neutron stars, potential black holes, and the enrichment of space with the elements necessary for future star and planet formation. Supernova 1987A stands as a testament to the dynamic and violent processes shaping our universe. Moving forward, we now shift our focus to an even more luminous and enigmatic phenomenon, one that channels the universe's raw energy with unmatched intensity: gamma-ray bursts. Moving forward, we delve into a phenomenon that outshines entire galaxies within seconds: gamma-ray bursts. These are the brightest and most powerful explosions ever detected in the universe, releasing more energy in a few moments than the sun would generate over its entire lifespan. Gamma-ray bursts are so intense that they can be observed from billions of light-years away, providing a glimpse into some of the most extreme events in cosmic history. But what causes these cataclysmic outbursts? Scientists have identified 2 primary origins: collapses of massive stars and mergers of neutron stars. In the first scenario, a massive star at the end of its life collapses under its own gravity, forming a black hole. This dramatic event generates powerful jets of energy that burst through the star's outer layers, producing the gamma rays we detect. In the second scenario, 2 neutron stars, ultra-dense remnants of collapsed stars, merge in a violent collision. The impact not only releases gravitational waves but also triggers a gamma-ray burst, sending energy rippling across the cosmos. What makes these bursts even more fascinating is their fleeting nature. Most gamma-ray bursts last only a few seconds to a few minutes, but their afterglows in other wavelengths, such as X-rays and visible light, can linger for days or even weeks, allowing astronomers to study their origin and environment. These events hold vast scientific importance, shedding light on the processes that create black holes, neutron stars, and heavy elements like gold and platinum. Despite their incredible brightness, gamma-ray bursts are incredibly rare, making each detection a groundbreaking opportunity to explore the extremes of physics and the violent beauty of the universe. From these extraordinary flashes of cosmic energy, we now turn our attention to an explosion much closer to home, one that dramatically reshaped life on our own planet, the CHICXULUB asteroid impact. Now turning to one of the most catastrophic explosions that ever struck our planet, we delve into the CHICXULUB asteroid impact. Approximately 66 million years ago, a colossal asteroid, estimated to be about 6 miles wide, slammed into what is now the Yucatan Peninsula in Mexico. The energy released by this impact was equivalent to billions of nuclear bombs detonating simultaneously. This unimaginable explosion triggered towering tsunamis, set vast swaths of the Earth's surface ablaze, and propelled enormous amounts of debris and vaporized rock into the atmosphere. As the dust and particles spread globally, they formed a thick, sun-blocking veil that plunged Earth into darkness and a dramatic cooling phase. This triggered a chain reaction of environmental devastation, collapsing ecosystems and wiping out roughly 75% of all species on Earth, including the dinosaurs. The long-term effects of the CHICXULUB impact were equally significant. The drastic climate changes caused by this event reshaped the planet's surface and marked the end of the Cretaceous period, paving the way for mammals to thrive and eventually dominate the evolutionary landscape. Today, the massive crater left behind by this ancient explosion serves as a haunting reminder of the destructive power of extraterrestrial impacts. With this tragic chapter of Earth's history in mind, we now turn our gaze back to the cosmos, to an explosion documented more than 1,000 years ago, the creation of the CRAB Nebula. Now turning to one of the most iconic cosmic explosions ever observed by humanity, we dive into the supernova that gave birth to the CRAB Nebula. Over 1,000 years ago, in the year 1054, ancient astronomers from around the world recorded an awe-inspiring event, a new star that suddenly appeared in the sky brighter than anything they had ever seen. This brilliant light in the constellation Taurus was visible even during the daytime for nearly a month and remained a prominent feature of the night sky for almost 2 years. What these early observers were witnessing was the explosive death of a massive star, an event we now call a supernova. This spectacular explosion scattered the star's outer layers into space, creating the intricate and colorful structure we know today as the CRAB Nebula. At the heart of this nebula lies a neutron star, a densely packed core left behind after the supernova. This rapidly spinning neutron star, or pulsar, emits beams of radiation as it rotates, acting like a cosmic lighthouse. The CRAB Nebula and its pulsar have provided astronomers with invaluable insights into the life cycle of stars, from their dramatic deaths to the formation of exotic objects like neutron stars. The observations of this event by ancient civilizations marked one of the earliest recorded instances of humanity documenting a supernova, offering a glimpse into the dynamic and ever-changing nature of the universe. With the story of this extraordinary stellar explosion illuminating our understanding of the cosmos, we now shift our focus to an even more magnificent type of cosmic event, the collision of two stars. Moving forward, we encounter one of the most breathtaking and energetic events in the cosmos: stellar collisions. Picture two colossal stars hurtling towards each other, drawn by the relentless pull of gravity. When they finally collide, the result is nothing short of extraordinary. The sheer force of the impact releases an unimaginable amount of energy, often outshining entire galaxies for a fleeting moment. These titanic explosions can lead to a variety of outcomes, depending on the size, type, and circumstances of the colliding stars. In some cases, the collision triggers the formation of a new star, a phoenix rising from the ashes of destruction. In other instances, the intense gravitational forces may give birth to a black hole, an object so dense that not even light can escape its pull. One remarkable example of a stellar collision is the event captured in the star system called V838 Monocerotis, often referred to as V838 Mon. This collision occurred roughly 5,000 light-years away and was observed in the early 2000s. The explosion released a dazzling burst of light and ejected massive amounts of material into space, forming a beautiful halo of glowing debris. Such events not only transform the local environment, but also play a significant role in shaping the dynamics of their host galaxy. Stellar collisions scatter heavy elements and other materials into the surrounding space, enriching the cosmic landscape and fueling the formation of future stars and planetary systems. These awe-inspiring interactions remind us of the raw, untamed power of the universe and its ability to create and destroy in equal measure. Having explored the explosive grandeur of stellar collisions, we now look towards a phenomenon on a galactic scale: the starburst galaxies that redefine cosmic fireworks. Now turning to the phenomenon of starburst galaxies, we enter a realm of cosmic activity so intense that it redefines what we know about the life cycle of stars. Starburst galaxies are regions where star formation occurs at an incredible pace, far exceeding that of typical galaxies. Imagine entire sections of a galaxy erupting with the birth of new stars, a process so vigorous that it creates shockwaves and powerful stellar winds. These winds, driven by the energy of newly forming and dying stars, sweep through the galaxy, carrying with them an array of elements forged deep within the stars themselves. But this rapid star formation comes at a cost. The overwhelming activity often triggers destructive explosions as massive stars live short, explosive lives. These stellar deaths in the form of supernova can release tremendous amounts of energy, disrupting the galaxy's delicate balance and scattering heavy elements like carbon, oxygen, and iron into interstellar space. This violent and chaotic process plays a crucial role in galactic evolution. The ejected materials serve as the building blocks for new stars, planets, and even life itself, enriching the surrounding space with the elements necessary for complex chemistry. Furthermore, the high levels of radiation and energy emitted by these galaxies can influence nearby structures, reshaping the cosmic environment on a grand scale. One of the most famous examples of a starburst galaxy is M82, also known as the Cigar Galaxy. Located around 12 million light-years away, M82 is a spectacular showcase of this phenomenon. Observations reveal vast, luminous outflows of gas and dust being expelled from its central regions, a direct result of the intense star-producing activity. Such galaxies remind us of the interconnected nature of the universe, where creation and destruction work hand in hand to drive the endless cycle of cosmic renewal. With the next phase of our journey in sight, we now turn our attention to a truly enigmatic event, the Great Eruption of Eta Carinii, an explosion unlike any other in our galaxy. With the next phase of our journey in sight, we focus on the extraordinary Great Eruption of Eta Carinii, an event that stands out as one of the most mysterious and powerful explosions ever recorded in our galaxy. Eta Carinii is no ordinary star. It is a supermassive star over 100 times the mass of our Sun, located roughly 7,500 light-years away in the Carina constellation. What makes this event so intriguing is that, unlike a typical supernova where a star meets its ultimate fate, Eta Carinii unleashed an enormous burst of energy in the mid-19th century and somehow survived the ordeal. This eruption released a staggering amount of energy, rivaling that of a supernova, ejecting a vast amount of its outer layers into space at speeds exceeding 2 million miles per hour. The expelled material formed a massive, glowing nebula known as the Homunculus Nebula, a hauntingly beautiful structure that continues to expand and shine to this day. What caused such a cataclysmic yet incomplete explosion remains a deep mystery in the study of massive stars. Scientists speculate that the eruption could have been triggered by interactions within a binary or even a triple star system, where immense gravitational forces destabilized Eta Carinii. Others suggest it was a rare event specific to hypergiant stars nearing the end of their lives. Whatever the case, this singular explosion defied expectations, challenging our understanding of how supermassive stars behave and evolve. The Great Eruption also shed light on the incredible energy such stars can release, without necessarily destroying themselves in the process, opening the door to further studies about the life cycle of these cosmic giants. Beyond its scientific intrigue, the aftermath of Eta Carinii's eruption offers a breathtaking glimpse into the dynamic forces at play in our galaxy. The homunculus nebula, with its twin-lobed structure of gas and dust, continues to be an astronomical wonder, a living testament to the power of this star. The intense radiation emitted by Eta Carinae and the surrounding nebula has transformative effects on the interstellar medium, enriching nearby regions with elements that could one day form new stars or planets. This explosion reminds us of the unpredictable nature of the universe, where stars like Eta Carinae can rewrite the rules of stellar physics. Moving forward, our cosmic exploration leads us to another fascinating phenomenon: the colossal energy unleashed by quasars, which takes us even deeper into the mysteries of the universe. Now turning to another breathtaking cosmic phenomenon, we delve into the world of quasars, some of the most energetic and enigmatic objects in the universe. Found at the heart of distant galaxies, quasars are powered by supermassive black holes, millions to billions of times the mass of our Sun. These extraordinary black holes feed on surrounding matter, pulling in gas, dust, and even whole stars with their immense gravitational pull. As this material spirals inward, it forms an accretion disk, a structure that generates incredible friction and heat as particles collide at near light speeds. This process releases an astonishing amount of energy, often outshining the combined light of all the stars in the host galaxy. What makes quasars truly fascinating is their dual role as both destructive and creative forces in the cosmos. The intense radiation and powerful jets emitted by quasars can sweep away nearby gas, halting star formation in their host galaxies. At the same time, they play a critical role in spreading heavy elements across intergalactic space, seeding the cosmos with the building blocks for future stars and planets. These energetic beacons are not just dazzling to observe, they are also invaluable tools for astronomers. Quasars serve as lighthouses, their brilliant emissions cutting through vast cosmic distances to provide snapshots of the young universe. By studying quasars, scientists can map the large-scale structure of the cosmos, uncovering the distribution of matter and the evolution of galaxies over billions of years. Beyond their scientific significance, quasars also deepen our understanding of black holes. They reveal how these mysterious objects grow and interact with their surroundings, offering clues about the formation of supermassive black holes shortly after the universe's birth. The study of quasars challenges the limits of our knowledge, pushing us to explore the mechanisms that fuel such explosive power and illuminating the interconnected tapestry of galaxies and black holes. Moving forward, our journey through awe-inspiring cosmic events continues with a look at a future collision on a galactic scale: the incredible meeting of the Andromeda and Milky Way galaxies. Moving forward, our gaze shifts to a breathtaking event predicted to unfold in the distant future: the dramatic collision between the Andromeda galaxy and our very own Milky Way. Set to occur approximately 4.5 billion years from now, this cosmic encounter is nothing short of a titanic clash of galactic proportions. Andromeda, the spiral galaxy currently hurtling towards us at over 200,000 miles per hour, is destined to merge with the Milky Way in a spectacle that will reshape both galaxies. Scientists have conducted detailed simulations of this colossal event, providing a mesmerizing glimpse into the chaotic beauty of galactic evolution. As the two galaxies approach one another, their gravitational forces will trigger massive disruptions, flinging stars, gas, and dust into dramatic tidal streams that stretch across millions of light years. The collision itself will not result in stars crashing into each other despite the billions of stars involved. The vast distances between them make direct impacts exceedingly rare. Instead, the gravitational turbulence will rearrange their orbits, creating a dazzling cosmic ballet. Clouds of gas will clash and compress, igniting bursts of star formation that illuminate the merging galaxies with new light. Over the course of several billion years, the once separate entities will settle into a single, unified galaxy, likely a giant elliptical structure astronomers have already named Milky. While our solar system is expected to survive this galactic upheaval, its location within the merged galaxy will change dramatically, possibly drifting even closer to the core of this new cosmic home. The Andromeda Milky Way collision is not just a story of destruction, it is also a transformative process, one that exemplifies the ever-evolving nature of the universe. By studying simulations of such events, scientists gain valuable insights into the mechanics of galaxy formation and the role of collisions in shaping the universe over time. This future phenomenon reminds us of the dynamic, interconnected nature of space, where even massive, seemingly eternal structures like galaxies are subject to change and renewal. As we marvel at the scale and beauty of this predicted event, our journey through the cosmos leads us to consider yet another incredible occurrence, the phenomenon of stellar winds colliding to create explosive cosmic shockwaves. Now turning to the phenomenon of stellar winds colliding, we encounter an extraordinary spectacle fueled by the immense power of massive stars. Stellar winds, which are streams of charged particles ejected from the outer layers of stars, travel at astonishing speeds, often reaching millions of miles per hour. When the winds from two massive stars collide, their combined energy creates an explosive interaction that sends shockwaves rippling through space. These shockwaves, in turn, compress and heat the surrounding gas to millions of degrees, generating powerful bursts of X-rays that can travel across unimaginable distances and be detected from Earth. The collision of stellar winds is more than just a dramatic phenomenon. It is a testament to the raw power of the cosmos. In systems containing two closely orbiting massive stars, also known as binary star systems, the collision zone where their winds meet becomes a hotbed of activity. The energy released in this zone is so intense that it can outshine the light of the stars themselves in certain wavelengths, making these systems crucial targets for astronomers studying high-energy processes in the universe. Observations of such events provide scientists with invaluable data about stellar compositions, the mechanics of wind generation, and the impact these interactions have on their surrounding environments. One compelling example of this phenomenon is the binary star system Eta Carinae, located over 7,500 light-years from Earth. Eta Carinae is home to two massive stars whose winds collide with ferocious intensity, creating some of the brightest and most powerful X-ray flares ever recorded. The extreme turbulence in their collision zone offers a rare glimpse into the life cycles of massive stars and the forces shaping their evolution. As we unravel the secrets of these stellar wind collisions, we continue to uncover profound insights into the processes that power our universe. From the dazzling X-rays emitted to the shockwaves that ripple across space, these collisions are a reminder of the relentless energy coursing through the cosmos. With this captivating display in mind, our journey now takes us deeper into the universe to explore the dramatic manifestations of magnetar flares explosions fueled by the most powerful magnetic fields known to exist. Moving forward, we arrive at one of the most extraordinary phenomena in the universe: magnetar flares. Magnetars are a rare type of neutron star, the dense remnants of massive stars that have undergone supernova explosions. What sets magnetars apart is their mind-boggling magnetic fields, the most intense known in the cosmos, billions of times stronger than the strongest magnets on Earth. These immense magnetic forces can twist and deform the magnetar's crust, triggering sudden and violent releases of energy known as magnetar flares. To put their power into perspective, a single flare from a magnetar can release more energy in just 1 second than the Sun generates over a span of 100,000 years. Such a staggering burst of energy is enough to send gamma rays and X-rays blazing across vast stretches of the universe. One of the most famous examples of a magnetar flare occurred on Earth's cosmic doorstep in the year 2004. Originating from a magnetar located about 50,000 light-years away in the constellation Sagittarius. The event, known as the Giant Flare of SGR 1806-20, was so powerful that it temporarily disrupted Earth's ionosphere, damaging satellites and briefly impacting radio communications. This flare is considered one of the brightest high-energy events ever detected within our galaxy, illustrating the nearly incomprehensible energy these celestial bodies can unleash. Magnetar flares not only demonstrate the destructive capabilities of the universe, but also provide scientists with crucial insights into the physics of extreme magnetic fields and the behavior of matter under such extreme conditions. By studying these flares, astronomers are not only exploring the life cycles of neutron stars, but also unlocking secrets about the universe's most extreme environments. With this understanding of magnetar flares, we now venture into another chapter of the cosmos explosive phenomena Tycho's supernova, a historical event that captivated humanity's curiosity and reshaped our understanding of the stars. Now turning to Tycho's supernova, we find ourselves rewinding the clock to the year 1572, when a brilliant new light suddenly appeared in the night sky. This wasn't just any celestial event. This was a supernova so luminous that it could be seen with the naked eye, even during the day. The awe-striking phenomenon was first noted by Danish astronomer Tycho Brahe, whose meticulous observations marked a turning point in the study of astronomy. At the time, the prevailing belief was that the heavens were unchanging and perfect, but the appearance of this new star, as it was called, shattered that notion. Tycho documented the event in great detail, noting its position and brightness over time, which eventually helped redefine humanity's understanding of the universe. What made this supernova so groundbreaking were the implications it held for the life cycles of stars. Scientists later identified Tycho's supernova as a type Ia supernova, a specific kind of explosion that occurs when a white dwarf star in a binary system accumulates too much material from its companion star. The resulting runaway nuclear reaction obliterates the white dwarf in a colossal burst of energy. Such explosions are not only mind-bogglingly powerful but also act as cosmic measuring tools thanks to their consistent peak brightness. This unique trait enables astronomers to calculate vast cosmic distances, contributing significantly to the study of the expanding universe. The remnants of Tycho's supernova, still observable in the form of an expanding shell of gas and debris, continue to be a vital area of research. Modern telescopes and instruments have allowed scientists to explore this remnant in unprecedented detail, uncovering more about the chemical compositions ejected during a supernova and the shockwaves that ripple through surrounding space. Over 4 centuries after its appearance, Tycho's supernova remains a cornerstone in the understanding of stellar evolution, showcasing how monumental explosions can rip apart stars yet contribute to the creation of new cosmic structures. As the legacy of Tycho's supernova illuminates our past, we now steer toward an explosive event that occurred much closer to home, the Great Cometary Collision that forever changed our view of planetary impact. Now turning to the Great Cometary Collision, we shift our focus to one of the most dramatic and visually stunning events ever observed in our solar system, the breakup of Shoemaker-Levy 9, and its impact with Jupiter in the year 1994. This celestial spectacle unfolded when the comet, once a single body, ventured too close to Jupiter's immense gravitational pull. The planet's powerful forces tore the comet apart into over 20 fragments, each destined for a fiery collision with its colossal host. Over the course of 6 days, these fragments pummeled Jupiter's atmosphere one by one, creating explosions so massive that their scars were visible from Earth through telescopes. Each impact released energy equivalent to millions of nuclear bombs, momentarily creating fireballs larger than the Earth itself. What made this event particularly groundbreaking was the unprecedented opportunity it provided to study planetary impacts in real time. Scientists eagerly observed as the comet's fragments struck Jupiter, leaving behind enormous, dark impact scars that lingered for months. These blemishes revealed invaluable insights into Jupiter's upper atmosphere and the chemical reactions triggered by such collisions. The event also highlighted the potential volatility of celestial objects and reminded us that our solar system is far from a tranquil place. The Shoemaker-Levy 9 collision emphasized the importance of understanding cometary compositions and trajectories, as well as planetary defense mechanisms to guard against similar events closer to home. While Jupiter, with its massive gravity, often acts as a protective shield by absorbing or deflecting incoming objects, this event underscored the potential for destructive impacts that could one day threaten Earth. It was a cosmic wake-up call, one that spurred ongoing efforts to track near-Earth objects and develop strategies to mitigate potential threats. As Shoemaker-Levy 9 etched its mark on Jupiter and on humanity's understanding of planetary collisions, we now turn to yet another fascinating cosmic eruption, one born from the unstable, luminous giants we call luminous blue variables, where stars explode in spectacular ways while defying the fate of total destruction. Now turning to the enigmatic luminous blue variables, we encounter a class of rare massive stars that are truly a spectacle of unpredictability and cosmic power. These stars, often described as ticking time bombs, are known for their violent and erratic outbursts, during which they shed enormous amounts of mass in the form of powerful stellar winds or cataclysmic explosions. Unlike supernova, these eruptions do not mark the end of the star's life, but rather serve as dramatic episodes in their tumultuous existence. Among the most famous examples of luminous blue variables is Eta Carinae, a colossal star in our galaxy whose great eruption in the mid-19th century remains one of the most studied stellar outbursts in astrophysics. This eruption released as much energy as a typical supernova, yet Eta Carinae survived the event and continues to shine today, cloaked in a magnificent cloud of ejected gas and dust known as the Homunculus Nebula. What makes luminous blue variables so fascinating is their contribution to the grand cycle of cosmic recycling. During their explosive outbursts, these stars disperse heavy elements like carbon, nitrogen, and oxygen into the surrounding interstellar medium, enriching the raw material from which new stars and planets are born. In this way, luminous blue variables play a crucial role in the chemical evolution of galaxies, ensuring that the ingredients for life and future celestial wonders are continually replenished. These unpredictable giants also serve as a natural laboratory for studying the physics of stellar winds, mass loss, and the mechanisms that drive extreme stellar behavior. However, the exact triggers behind their violent eruptions remain a puzzle for astronomers. Some theories suggest that rapid internal changes or instabilities in the star's core could lead to these outbursts, while others point to interactions with companion stars in binary systems. Whatever the cause, luminous blue variables remind us of the immense forces at work in the universe and the delicate balance that governs the lives of stars. As we witness their breathtaking displays of power and ponder their mysteries, we move forward to explore yet another astonishing example of stellar theatrics, a star's eventual death as it ignites in the explosive brilliance of a nova, a phenomenon that, while less intense than a supernova, reveals remarkable insights into the lives of binary stars. Moving forward, we delve into the captivating phenomenon of nova events, a less intense yet profoundly intriguing display of cosmic power. Unlike the cataclysmic force of a supernova, a nova is a more controlled yet no less spectacular eruption of light and energy. These events occur in binary star systems where two stars are gravitationally bound, with one being a dense and compact white dwarf. Over time, the white dwarf draws matter, primarily hydrogen, from its companion star through a process known as accretion. As this hydrogen accumulates on the white dwarf's surface, it is compressed by the dwarf's intense gravity, creating extreme temperatures and pressures. Eventually, a critical point is reached, sparking a runaway thermonuclear reaction that ignites the accumulated gas in a brilliant burst of energy. This explosion, though much less powerful than a supernova, is still awe-inspiring, temporarily increasing the star's brightness by thousands of times. To an observer on Earth, it appears as a sudden, dramatic brightening of what was previously a faint or invisible star. What makes nova particularly fascinating is that the white dwarf often survives this event, leaving it capable of repeating the process, sometimes multiple times over its life. Some binary systems have been observed producing recurrent nova, showcasing the cyclical and enduring nature of this phenomenon. Beyond their visual splendor, nova offer valuable insights into the physics of accretion, nuclear reactions, and binary star dynamics. They also contribute to the enrichment of the interstellar medium by ejecting elements like helium, carbon, and nitrogen, albeit on a smaller scale compared to their mightier supernova cousins. These explosions, therefore, play a subtle yet significant role in the cosmic cycle of matter, distributing material that can one day become part of new stars, planets, or even life itself. As we marvel at these periodic bursts of energy and their impact on the universe, we now turn our attention to a much-anticipated event that promises to be one of the most dazzling cosmic spectacles of our time: the potential explosion of Betelgeuse, a red supergiant star on the brink of its final act. Now turning to the potential cosmic fireworks that have astronomers and stargazers alike on the edge of their seats, we explore the inevitable fate of Betelgeuse, one of the most famous red supergiant stars visible in our night sky. Nestled in the constellation of Orion, Betelgeuse has long intrigued scientists with its immense size and advanced stage of stellar evolution. This colossal star, estimated to be over 700 times the size of our Sun, is nearing the end of its life, poised to explode as a supernova, potentially within the next few 100,000 years, a mere blink in cosmic terms. The anticipation surrounding Betelgeuse's demise is fueled by the unprecedented opportunity it presents to observe a supernova event in extraordinary detail, as this star lies relatively close to us, a mere 600 light-years away. When Betelgeuse eventually collapses under its own gravity, the resulting explosion will be nothing short of spectacular. It is expected to release an unimaginable amount of energy, briefly outshining the combined brilliance of billions of stars in the Milky Way galaxy. To an observer on Earth, the explosion would appear as a blazing point of light in the sky, potentially visible during daylight hours and casting noticeable shadows at night. Beyond its dazzling display, such a nearby supernova would offer a rare and invaluable chance to study the intricate mechanics of stellar death, from the formation of neutron stars or black holes to the dispersal of heavy elements crucial for the building blocks of planets and life. Betelgeuse has given us many clues that its end is near. In recent years, the star has shown unusual dimming and brightening, sparking speculation among scientists and enthusiasts about its imminent collapse. While these fluctuations are likely caused by the star's complex surface activity and dust clouds, they serve as reminders of the dynamic and unpredictable nature of dying stars. Whenever the moment comes, the event will be a landmark in human history, captivating not only professional astronomers but also people around the world, as we collectively bear witness to one of the universe's grandest finales. With excitement building around Betelgeuse's eventual transformation into a supernova, let us now venture further into the unexplored frontiers of space to uncover the mysterious disruptions that may arise from the distant reaches of the Oort cloud, where dormant comets could one day bring their own explosive tales to our solar system. Moving forward, we journey to the farthest reaches of our solar system, an enigmatic region known as the Oort cloud. This vast spherical shell of icy bodies encircling the Sun lies tens of thousands of times farther away than the Earth is from the Sun, serving as a distant reservoir of long-period comets. While the Oort cloud itself might seem quiet and uneventful, its dormant inhabitants have the potential to ignite chaos within our solar system, thanks to gravitational disruptions that could send comets hurtling inward at breakneck speeds. Such disruptions could be triggered by passing stars, rogue planets, or even the subtle gravitational tides of the Milky Way galaxy. these once tranquil objects on a collision course with the inner solar system could result in explosions of cataclysmic proportions upon impact with planetary bodies. The effects of such an event would depend on the size and speed of the incoming comet. A direct impact on Earth by a sufficiently large Oort cloud comet could unleash energy surpassing millions of megatons of TNT, dwarfing even the asteroid collision that wiped out the dinosaurs. The explosion would cause widespread destruction, generate global shockwaves, and inject vast amounts of dust and debris into the atmosphere, potentially triggering a long-lasting impact winter that could alter Earth's climate and threaten life as we know it. Even a close pass from a large comet without a direct hit could still result in significant gravitational disturbances and dazzling meteor showers, leaving a profound impact on the dynamics of the solar system. Beyond the immediate danger, such events provide crucial opportunities for scientists to study the composition and origins of these ancient wanderers, many of which hold clues to the birth of our solar system. Oort cloud objects are considered pristine relics, largely unchanged since their formation billions of years ago. By examining the materials deposited by these icy visitors, researchers could unlock new insights into the early conditions that gave rise to planets and potentially life itself. While the likelihood of a major cometary impact within our lifetimes remains low, the universe has an uncanny way of surprising us, and the Oort cloud serves as a powerful reminder of the dynamic and interconnected nature of celestial mechanics. With this in mind, we now leave the icy edges of the solar system to delve into the mysterious gamma-ray emitting structures lurking in and around the Milky Way's core, known as the Fermi bubbles, where explosive cosmic activity unfolds on a galactic scale. Now turning to the heart of our galaxy, we encounter one of the most astonishing and enigmatic phenomena in the Milky Way massive structures known as the Fermi bubbles. These colossal, gamma-ray emitting formations span tens of thousands of light years both above and below the galactic core, resembling immense cosmic balloons that stretch far beyond the plane of the galaxy. Discovered over a decade ago, the Fermi bubbles are believed to be remnants of explosive activity originating from the supermassive black hole at the center of the Milky Way, a region teeming with intense gravitational forces, swirling gas, and powerful magnetic fields. While the exact cause of their formation remains a mystery, scientists have proposed a few compelling theories. Some suggest they could be the aftermath of a titanic outburst from the central black hole, perhaps caused by it devouring a significant amount of matter in a relatively short time frame. Others speculate that the bubbles might stem from rapid star formation near the galactic core, which could have driven energetic winds and shockwaves capable of creating such massive structures. Whatever their origin, the amount of energy required to produce the Fermi bubbles is almost unimaginable, equating to millions of supernova explosions. What makes these cosmic fireworks even more fascinating is the detailed information they contain about our galaxy's past. The gamma rays emitted by the Fermi bubbles allow researchers to study high-energy processes that have shaped the Milky Way over millions of years. By analyzing these emissions, scientists gain insights into how galaxies evolve, how supermassive black holes interact with their surroundings, and how the flow of energy and matter influences star formation across vast distances. Observing the Fermi bubbles also provides a rare opportunity to glimpse the lasting effects of events that unfolded long before humanity existed. As we marvel at the scale and significance of these gamma-ray structures, the Fermi bubbles remind us of the extraordinary power residing at the heart of our own galaxy. They stand as cosmic signposts to a time of explosive activity that shaped the Milky Way as we know it today. Moving forward from the sweeping grandeur of galactic fireworks, we delve into an equally dramatic and rare event in the cosmos, the explosive collapse of massive stars directly into black holes known as Quasars. Prepare to uncover the incredible forces at play when the very fabric of a star is torn apart in a violent, fiery descent into oblivion. Now turning to the cataclysmic phenomenon of collapsars, we find ourselves confronting one of the most extreme and awe-inspiring events in the universe. Collapsars occur when the core of a massive star, far larger than our Sun, reaches the end of its nuclear fuel supply and collapses under its own overwhelming gravity. Rather than ending in a typical supernova explosion, the star's core undergoes a spectacular and violent transformation, plunging directly into a black hole. This extraordinary process unleashes tremendous amounts of energy in the form of high-energy jets and gamma-ray bursts, some of the brightest and most powerful explosions ever detected. What makes collapsars so unique is the sheer violence of their collapse and the incredible forces they release. As the star's core falls inward, it forms a rapidly spinning disk of intensely hot gas and dust around the newly created black hole. From this chaotic maelstrom, twin jets of high-energy particles are launched at nearly the speed of light, piercing through the outer layers of the star and into the surrounding space. These jets produce gamma-ray bursts that can outshine entire galaxies for brief moments, making them visible across vast cosmic distances. Scientists study collapsars not only for their dramatic displays, but also for the valuable clues they provide about black hole formation and the extreme physics of the universe. The energy released during a collapsar event is so immense that it can create and disperse some of the heaviest elements in the periodic table, like gold and platinum, enriching the surrounding interstellar medium. Additionally, observing these events helps astronomers better understand the life cycles of massive stars and the intricate processes that govern their explosive deaths. The rarity of collapsars adds to their mystery and allure. They remind us of the profound forces at work in the cosmos, forces capable of creating and destroying in equal measure. As we venture deeper into the mysteries of these extraordinary explosions, we realize just how much they reveal about the interconnectedness of the universe and the unrelenting power of gravity. With this glimpse into the fiery chaos of collapsars, we now turn our attention to yet another type of cosmic explosion that marks the birth of celestial giants, the violent processes that ignite the formation of stars themselves. Prepare to be amazed as we unravel the explosive origins of starlight that illuminate the universe. Now turning to the explosive birth of stars, we delve into the fascinating and chaotic processes that spark the creation of celestial giants. Stars, the luminous beacons of the universe, begin their lives in vast, dense clouds of gas and dust known as nebulae. These stellar nurseries may appear calm and serene from a distance, but they are actually teeming with dynamic activity and violent forces. The journey from a simple cloud of gas to a radiant star begins when gravitational forces pull the cloud's material inward, causing it to collapse. This collapse triggers a chain reaction, heating the dense core and compressing it under immense pressure. As the temperature and pressure within the core rise, nuclear fusion ignites a process where hydrogen atoms fuse together to form helium, releasing a tremendous amount of energy in the form of heat and light. But before this fusion begins, the collapse itself can produce shock waves that ripple through the surrounding material, creating dramatic bursts of energy and light. These shock waves can even trigger the formation of neighboring stars, spreading the cycle of creation across a nebula. In many cases, external events such as supernova explosions nearby can further compress these clouds, kickstarting their collapse and accelerating star formation. The birth of a star is not a quiet event but rather a spectacular explosion of energy, marked by intense bursts of light and powerful outflows of gas. These outflows, called stellar winds, sweep away the remaining gas and dust, revealing the newly formed star. This process of creation can illuminate entire regions of space, producing breathtaking phenomena like reflection nebulae and bright star clusters. For astronomers, studying these stellar nurseries offers valuable insights into the early stages of a star's life cycle, the conditions required for star formation, and the role these processes play in the evolution of galaxies. What makes the explosive birth of stars even more extraordinary is its contribution to the universe's chemical diversity. During their formation, stars inherit and later distribute elements formed in previous generations of stars, ensuring that the cosmic cycle of matter continues. The light from young stars also energizes the surrounding nebulae, making them glow vividly and rendering the birthplaces of stars some of the most visually stunning regions in the cosmos. With every star that is born, a new chapter begins in the story of the universe. These fiery origins remind us of the immense power and beauty at work in the cosmos, creating light where there was once darkness. As we marvel at the explosive processes behind star formation, our journey continues to yet another breathtaking explosion, one that holds secrets of historical significance. We now shift our focus to the awe-inspiring event of Kepler's supernova and the lessons it has taught us about the transient and powerful nature of the stars. Now turning to the explosion of Kepler's supernova, we revisit one of the most remarkable astronomical events ever recorded. In the year 1604, this extraordinary stellar explosion lit up the night sky so brightly that it was visible to the naked eye for several weeks, even during the daytime. Known as SN 1604, or simply Kepler's supernova, this incredible event occurred in the constellation Ophiuchus and was the last supernova observed in our galaxy. Named after the renowned astronomer Johannes Kepler, who meticulously documented its appearance and behavior, this event has since become a cornerstone in the study of stellar explosions. Kepler's observations of the supernova played a crucial role in advancing our understanding of these cosmic phenomena. At the time, the concept of a supernova was not understood, and such events were often seen as mysterious omens. However, Kepler's detailed records of the brightness, color changes, and duration of the explosion provided early scientists with invaluable data. These observations laid the groundwork for identifying and classifying supernova as a distinct type of stellar event. Modern astronomers now know that Kepler's supernova was a type Ia supernova, an explosion that occurs in a binary star system when a white dwarf accumulates enough material from its companion star to trigger a runaway nuclear reaction. These explosions release an immense amount of energy, outshining entire galaxies and creating shockwaves that sweep through space. The remnants of SN 1604, although faint today, still offer clues about the surrounding environment and the processes that occur in such cataclysmic events. The study of Kepler's supernova has provided insights not only into the life cycles of stars, but also into the expansion of the universe itself. Type Ia supernova are used as standard candles by astronomers because their brightness is consistent and predictable, allowing scientists to measure vast cosmic distances with remarkable accuracy. This discovery has been instrumental in understanding the universe's accelerating expansion, a finding that reshaped modern cosmology. Kepler's supernova serves as a timeless reminder of the transformative power of the cosmos and the science it inspires. From its dazzling brilliance over 4 centuries ago to its enduring impact on our understanding of supernova, this explosion remains a testament to the ever-evolving story of the universe. With the lessons from Kepler's supernova in mind, we now venture into an even grander spectacle, exploring the colossal energy unleashed during galaxy cluster collisions and the clues they hold about the mysterious dark matter. Moving forward, we arrive at one of the most awe-inspiring cosmic phenomena: galaxy cluster collisions. Imagine clusters of galaxies, each containing hundreds or even thousands of galaxies, hurtling toward each other at mind-boggling speeds. When these colossal entities collide, the energy released is almost unimaginable, producing some of the most powerful explosions in the universe. A prime example of this is the Bullet Cluster, located approximately 3 billion light-years from Earth. The Bullet Cluster collision is not just a breathtaking event in terms of energy, but also a critical piece in the puzzle of understanding one of the universe's greatest mysteries: dark matter. As these clusters collide, their hot, ionized gas is heated to extreme temperatures and emits intense X-rays detectable from Earth. However, what truly sets events like the Bullet Cluster apart is what they reveal about the elusive dark matter. Astronomers have observed that the visible matter from the colliding galaxies behaves quite differently from the rest of the cluster's mass. Using gravitational lensing, a technique that measures how massive objects bend light, scientists have discovered that most of the mass in these collisions does not come from visible matter but from something invisible: dark matter. In the case of the Bullet Cluster, this is evident as the visible gas lags behind the dark matter, which passes through the collision almost untouched, creating a separation between them. This separation provides striking visual evidence of dark matter's existence and behavior, offering insights that cannot be gathered from studying ordinary matter alone. The collision of galaxy clusters serves as a massive laboratory, allowing scientists to study how dark matter interacts, or does not interact, with itself and other types of matter. Such research has brought us closer to understanding the nature of dark matter, a substance that makes up approximately 27% of the universe but remains one of its greatest enigmas. The Bullet Cluster and similar collisions not only help unravel the mysteries of dark matter, but also shed light on the origins and evolution of large-scale cosmic structures. These cataclysmic events are a testament to the dynamic and ever-changing nature of the universe. As we marvel at the enormous energy and complexity of galaxy cluster collisions, we move next to explore an even rarer and more devastating phenomenon in the cosmos: the titanic explosions known as pair instability supernova. Now turning to one of the rarest and most incredible phenomena in the cosmos, we delve into the staggering power of pair instability supernova. These extraordinary explosions occur under very specific conditions when a massive star, one with a core mass between 65 and 130 times that of our Sun, reaches the end of its life. At this critical point, the star's core becomes so hot that it starts producing pairs of particles and their antiparticles, known as electrons and positrons. This process steals energy from the core, disrupting the delicate balance between the outward pressure of radiation and the inward pull of gravity. As the balance collapses, gravity takes over and the star begins to implode. But unlike typical supernova, where the core might collapse into a neutron star or black hole, a pair instability supernova takes a dramatically different path. The implosion triggers a runaway thermonuclear reaction, releasing an unimaginable amount of energy in an instant. The result is a cataclysmic explosion so powerful that the star is completely obliterated, leaving no remnant behind, not even a black hole. Instead, the entire star is blown apart, scattering its elements across the cosmos. What makes these explosions particularly fascinating is their immense energy output, far surpassing that of regular supernova. The light from a pair instability supernova can shine brighter than an entire galaxy for weeks or even months, reaching distances so vast that they can be observed billions of light-years away. These rare explosions also play a crucial role in the universe by spreading heavy elements like oxygen, carbon, and iron into the surrounding space, seeding the building blocks for future stars, planets, and even life itself. Such events are believed to have been more common in the early universe, when massive metal-poor stars were more prevalent. Today, they are thought to be exceedingly rare, but studying them offers a window into the conditions of the cosmos in its infancy. Through pair instability supernova, scientists gain invaluable insights into the life cycles of the universe's most massive stars, as well as the processes that enrich the cosmos with the elements essential for life. With their sheer scale and profound implications, these explosions stand as a potent reminder of the universe's boundless potential for both destruction and creation. And as we reflect on the cosmic significance of these rare events, we move forward to explore yet another spectacular aftermath of stellar death: the gigantic remnants left behind by the Vela supernova. Now turning to the colossal aftermath of the Vela supernova, we uncover the incredible story of the Vela supernova remnant and the pulsar it left behind. Approximately 11,000 years ago, a massive star in our galaxy met its cataclysmic end in a supernova explosion of unimaginable power. What remains today is the Vela supernova remnant, an expansive cloud of gas and dust glowing brightly across multiple wavelengths, from visible light to X-rays, revealing the violent past of this extraordinary event. At the heart of this cosmic debris lies the Vela pulsar, a rapidly rotating neutron star, which serves as a living testament to the immense forces unleashed during the supernova. The Vela pulsar captivates astronomers with its precision. It rotates at an astonishing rate of over 11 times per second, emitting beams of electromagnetic radiation like a cosmic lighthouse. These beams sweep across space, and when they align with Earth, they appear as pulses of light, hence the name pulsar. The formation of such a neutron star is a remarkable process. When the core of the original massive star collapsed, the extreme density and gravity compressed it into a sphere no larger than a city, yet with a mass greater than the Sun. This process also conserved the star's angular momentum, causing the pulsar to spin at incredible speeds. What makes the Vela supernova remnant and its pulsar scientifically invaluable is the insight they provide into the physics of neutron stars and supernova explosions. The high-energy particles and radiation emitted by the Vela pulsar allow researchers to better understand the extreme states of matter that occur within neutron stars, conditions so intense that they cannot be replicated on Earth. Additionally, the interactions between the pulsar's powerful magnetic field and the surrounding remnant help illuminate the mechanisms that shape the formation and evolution of pulsars. The Vela supernova remnant also plays a crucial role in enriching the surrounding space with elements forged in the heart of the original star. These heavy elements, scattered far and wide by the explosion, contribute to the formation of new stars, planets, and even the chemistry of life. Observing the Vela remnant and its pulsar not only helps us piece together the life cycle of massive stars, but also brings us closer to understanding the intricate tapestry of the cosmos. As we marvel at the lingering echoes of this ancient explosion, we are reminded of the immense power and complexity of the universe's most destructive events. And with the Vela supernova remnant offering such a profound glimpse into the aftermath of stellar death, we now shift our focus to an enigmatic phenomenon that has baffled astronomers for years: the mysterious bursts of energy known as fast radio bursts. Now turning to the mysterious phenomenon of fast radio bursts, we find ourselves exploring one of the universe's most puzzling and awe-inspiring events. Fast radio bursts are brief yet extraordinarily powerful pulses of radio waves that last only a few milliseconds. Despite their fleeting nature, they release as much energy in that short time as the Sun emits over several days. These high-energy bursts are detected from immense distances, often billions of light-years away, making them one of the most powerful cosmic signals ever recorded. What makes fast radio bursts so intriguing is not just their intensity, but also the deep mystery surrounding their origins. Scientists have proposed several theories to explain these enigmatic signals. One leading hypothesis suggests that some fast radio bursts might be the result of collisions between neutron stars. When two neutron stars merge, they release a tremendous amount of energy, potentially producing these intense bursts of radio waves. Another compelling theory links fast radio bursts to magnetars, which are a type of neutron star with an extraordinarily strong magnetic field. Magnetars are known to release bursts of high-energy radiation due to their unstable magnetic fields, and some researchers believe these violent outbursts could account for certain fast radio bursts. Adding to the mystery, a few fast radio bursts have been observed to repeat, coming from the same source at irregular intervals. This has led scientists to consider other possibilities, such as starquakes on the surface of magnetars or unknown processes in highly active galactic environments. The repeating behavior suggests a more gradual mechanism rather than a one-time catastrophic event like a collision. However, the precise causes remain elusive, and fast radio bursts continue to challenge our understanding of the cosmos. Beyond their origins, these bursts are also valuable cosmic tools. Because fast radio bursts travel across vast distances, they pass through intergalactic space where they interact with the matter in their path. The way these signals disperse and change during their journey provides astronomers with clues about the density and composition of the universe between galaxies, offering a unique method for studying the cosmic web. As we delve deeper into the enigma of fast radio bursts, we uncover a glimpse of the universe's fascinating extremes and the questions that drive our quest for knowledge. And while these mysterious bursts have yet to reveal all their secrets, they push the boundaries of what we know and remind us of how little we still understand about the cosmos. Moving forward, let us now examine one of the most groundbreaking astronomical events of recent years, the first ever observed merger of two neutron stars and its spectacular consequences. Now turning to the groundbreaking event of the first observed neutron star merger, we dive into a moment in 2017 that reshaped our understanding of the universe. This extraordinary collision not only confirmed long-held theories but also unlocked entirely new ways of observing cosmic phenomena. When two neutron stars spiral toward each other and finally collide, the energy released is nothing short of phenomenal. In this particular event, known as GW 170817, scientists detected both gravitational waves and electromagnetic signals, a first in astronomy. Gravitational waves, ripples in the very fabric of space-time, were first theorized more than a century ago, but observing them alongside visible light and other forms of radiation marked a revolutionary leap forward. The aftermath of this merger offered unparalleled insights. As these dense remnants of massive stars collided, they produced an immense explosion known as a kilonova. This explosion unleashed energy equivalent to that of a supernova and gave rise to the synthesis of some of the universe's heaviest elements, including gold and platinum. It is astonishing to think that the gold in a wedding ring or the platinum in a watch might originate from such an event billions of years ago. Observing this cosmic alchemy confirmed that neutron star mergers are a primary source of heavy elements scattered throughout the universe. Adding to its significance, this neutron star collision was localized to a galaxy roughly 130 million light-years away, relatively close by cosmic standards. The combination of gravitational wave detectors and telescopes around the world enabled scientists to pinpoint its location and study it in unprecedented detail. This event marked the dawn of multi-messenger astronomy, where signals like gravitational waves and light are combined for a more comprehensive understanding of celestial events. It was a vivid demonstration of how interconnected the cosmos is, as a single event rippled across space and time, sending messages in more than one form to our instruments here on Earth. But the implications went beyond the event itself. This merger also confirmed predictions made by Einstein's theory of general relativity, as the observed gravitational waves behaved exactly as expected. It provided a direct link between neutron star mergers and short gamma-ray bursts, solving a long-standing mystery about the origins of these incredibly powerful explosions. The event underscored the critical role of international collaboration in astronomy, as observatories and detectors across the globe worked together to piece together the story of this cosmic collision. As we reflect on the profound revelations of this first observed neutron star merger, it becomes clear how such events not only deepen our scientific understanding but also connect us to the universe on a fundamental level. With every ripple in space-time and every photon of light, we are reminded of the dynamic and ever-changing nature of the cosmos. Moving ahead, let us now explore a fascinating and speculative realm by delving into the possibility of explosions driven by dark matter annihilation. a concept that may hold entirely new insights into the fabric of the universe. Now turning to the intriguing concept of dark matter annihilation, we step into the realm of theoretical physics and explore a phenomenon that could redefine our understanding of the universe's most elusive substance. Dark matter, which makes up approximately 85% of all matter in the universe, remains one of the greatest cosmic mysteries. It neither emits nor absorbs light, making it invisible to traditional telescopes. Yet, its gravitational effects reveal its presence, influencing the motion of galaxies and the structure of the cosmos itself. But what happens when particles of dark matter collide or annihilate each other? Scientists theorize that such interactions could release enormous amounts of energy, potentially producing detectable gamma rays or other high-energy signals. If dark matter particles do annihilate, their collisions might resemble explosive events on a cosmic scale. Picture streams of these mysterious particles in the dense cores of galaxies, colliding and transforming their mass into bursts of energy. These explosions could release gamma rays, the highest energy form of light, which our instruments might be able to detect. In fact, certain unusual gamma ray signals observed in the centers of galaxies have sparked speculation about whether they could be footprints of dark matter annihilation. These signals challenge explanations based on known astrophysical phenomena, leading some scientists to wonder if they might be indirect evidence of this enigmatic process. One of the most tantalizing aspects of dark matter annihilation is its potential to provide answers to long-standing questions. If such explosions were confirmed, they would not only reveal the nature of dark matter particles, but also shed light on how they shaped the early universe. Their energy output could help us understand large-scale structures like galaxy clusters and the mysterious web of matter connecting them. While this remains speculative, ongoing research using sophisticated gamma-ray detectors and space-based telescopes like the Fermi Gamma-Ray Space Telescope continues to search for telltale signals amid the vast cosmic background. The search for evidence of dark matter annihilation is a reminder of how science thrives on curiosity and the drive to uncover the unknown. Even without definitive proof, the mere possibility of such explosions challenges us to refine our instruments and expand our understanding of the universe's unseen components. As scientists scour the skies for further clues of these theoretical detonations, we are reminded that every mystery solved brings us closer to understanding the intricate tapestry of existence. With the speculative realm of dark matter annihilation sparking our imagination, we now turn our attention to a more familiar yet equally fascinating event, the eventual demise of our own sun. This colossal transformation will one day mark the end of an era, reshaping our solar system and offering yet another glimpse into the life cycle of stars. Now turning to the sun's inevitable fate, we enter a chapter that lies billions of years into the future, but holds profound significance for our understanding of stellar evolution. Like all stars, the sun has a finite lifespan, and its eventual demise is a dramatic yet natural conclusion to its existence. As it exhausts the hydrogen fuel that has powered it for billions of years, the sun will undergo a remarkable transformation. First, it will expand into a red giant, engulfing the inner planets, potentially including Earth, in a fiery, swollen mass. This phase will be marked by the sun shedding its outer layers in waves of intense stellar winds, ejecting material into the surrounding space and leaving behind a bright, glowing shell of gas known as a planetary nebula. This planetary nebula, while fleeting on a cosmic timescale, will serve as a spectacular reminder of the sun's once vibrant life. The outer layers, now scattered across the cosmos, will enrich the surrounding space with elements the sun forged during its lifetime, contributing to the ongoing cycle of star formation. At the heart of the nebula, a dense remnant will emerge, a white dwarf, essentially the exposed core of the sun. This white dwarf, no longer capable of nuclear fusion, will gradually cool and fade over trillions of years, becoming a faint shadow of its former glory. The sun's end is not just a story of destruction, but one of renewal. By releasing its material into the universe, it plays a part in seeding the galaxy with the building blocks necessary for future stars, planets, and potentially even life. Observations of similar stellar deaths, such as the Helix Nebula or the Ring Nebula, give us a glimpse of what our sun's final act might look like, stunning reminders of how intimately connected we are to the broader processes of the cosmos. As we reflect on the sun's eventual demise, it is humbling to consider how this event will reshape the solar system. Planets like Jupiter and Saturn may survive as cold, distant wanderers, orbiting a faint white dwarf that once was our brilliant star. The Earth, if it still exists, will likely become a scorched, barren world or be consumed entirely during the sun's red giant phase. Yet, while this chapter marks the end of an era, it is also a continuation of the universe's eternal story of transformation and creation. With the sun's final days offering a poignant look at the life cycle of stars, we now shift our focus to an explosive legacy, how such monumental events leave a lasting imprint on the fabric of the cosmos itself. Now turning to the legacy of the sun's ultimate demise, we begin to unravel an extraordinary tale of cosmic transformation. The sun's death will leave a profound and lasting imprint on the solar system, reshaping its very essence and scattering the seeds of a new beginning. As the sun sheds its outer layers, these ejected materials will not simply vanish. Instead, they will enrich the vast expanse of space with heavier elements, such as carbon and oxygen, which the sun forged during its lifetime. These elements are the very building blocks of planets, moons, and even life itself, ensuring that the sun's death will contribute to the birth of future stars and planetary systems elsewhere in the galaxy. For Earth, however, this will be the final chapter. If not consumed during the sun's red giant phase, our planet will likely be stripped of its atmosphere, left as a silent, barren husk orbiting the faint glow of the white dwarf that once lit its skies. Other planets like Jupiter and Saturn may endure as icy remnants, their once familiar orbits now shrouded in the cold vastness of space. Their continued existence as ghostly wanderers will serve as a testament to the sun's enduring gravitational pull, even in its diminished state. The asteroid belt, comets, and other celestial bodies will also bear the marks of change, their surfaces scarred by exposure to the sun's final outbursts. Yet this seeming end is anything but final. The sun's dispersal of elemental material will not only create a stunning planetary nebula, but also enrich future star-forming regions in other parts of the galaxy. Over millions of years, these elements will find their way into new stars, planets, and even the potential for life, recycling the sun's legacy into the fabric of the universe itself. The remnants of our solar system's central star will continue to participate in the grand cycle of stellar life and death, a reminder of the interconnectedness of all cosmic phenomena. As the once vibrant solar system enters a quieter phase, it merges into the eternal rhythm of the cosmos. The white dwarf, cooling over unimaginable spans of time, will eventually fade into obscurity, becoming a dark, inert remnant known as a black dwarf. A state theorized but not yet observed, as the universe is not old enough for any black dwarfs to exist. This slow fading marks the closing of one chapter, but the materials released by the sun will persist, woven into the ongoing story of the cosmos. Through its death, the sun ensures its contributions to the next generation of celestial wonders, leaving us with a profound understanding of our place in this vast, ever-evolving universe. With this renewed appreciation for how stars shape the cosmos long after their fiery end, we now turn to another astonishing cosmic spectacle, one that involves the explosive collision of entire galaxies, revealing yet another layer of the universe's dynamic story. Now turning to the anticipated aftermath of Betelgeuse's long-awaited supernova, we find ourselves standing on the brink of one of the most fascinating events that modern astronomy could ever witness. When Betelgeuse finally reaches the end of its life and erupts in a supernova, the explosion will not only light up our skies for weeks, perhaps even months, but it will also leave behind remnants that reshape our understanding of stellar death. At the heart of this aftermath, scientists predict the formation of either a neutron star or, if Betelgeuse's mass proves sufficient, a black hole. Neutron stars are some of the densest objects in the universe, where matter is compressed so tightly that even a sugar cube-sized portion would weigh as much as a mountain. If Betelgeuse creates one of these cosmic marvels, it would allow astronomers to study its properties more closely, providing invaluable insights into the nature of matter under extreme conditions. Alternatively, if the explosion is powerful enough, it could collapse into a black hole, a gravitational force so intense that not even light can escape. But the story does not end there. The supernova itself will release an incredible amount of energy, blasting surrounding space with shockwaves and scattering heavy elements like iron, gold, and even uranium across vast distances. These elements, forged in the heart of Betelgeuse and expelled during its fiery death, will enrich the interstellar medium, seeding the potential for new stars and planets in the future. The shockwaves from the explosion will also compress nearby gas clouds, potentially triggering the formation of entirely new star systems. This means Betelgeuse's demise is not merely the end of a single star, but rather the beginning of multiple cosmic journeys waiting to unfold. Closer to home, the explosion will also have a profound impact on its immediate surroundings, particularly the massive shells of gas and dust that Betelgeuse has already ejected during its unstable final years. These materials will interact with the supernova's shockwaves, producing luminous and intricate patterns that could light up the skies in ways we can only begin to imagine. For Earth, lucky enough to be at a safe distance of approximately 600 light-years, the supernova poses no direct threat but promises to deliver one of the most spectacular celestial shows in recorded human history. Imagine gazing up at the night sky and seeing a star so bright it rivals the moon, a glowing beacon that serves as a reminder of the immense power and beauty of the universe. This explosion, though seemingly destructive, is a vital part of the cosmic life cycle, ensuring that the elements forged in Betelgeuse's core become part of the building blocks of future stars, planets, and perhaps even life. Its remnants, whether a neutron star or a black hole, will continue to influence their surroundings for millions, even billions of years, pulling nearby matter into their gravitational embrace or emitting bursts of energy detectable across vast stretches of space. Betelgeuse's supernova will be a rare and extraordinary event, one that scientists eagerly await not only for its visual splendor, but also for the wealth of knowledge it will provide about the processes that govern our universe. With this breathtaking anticipation of Betelgeuse's future explosion, we move forward to explore yet another astronomical marvel. Imagine what happens when colossal forces collide on a truly cosmic scale, as we delve into the explosive spectacle of galaxy cluster collisions. As we conclude this journey through the cosmos, we are left in awe of the sheer diversity and unimaginable power of the explosions that shape our universe. From the cataclysmic beginnings of the Big Bang to the dramatic supernova that forged the elements of life, and the breathtaking energy of gamma-ray bursts that outshine entire galaxies, each event serves as a reminder of the dynamic and ever-changing nature of space. These explosive phenomena are not merely destructive, they are the universe's way of creating, transforming, and sustaining the cosmic order. Through understanding these events, scientists uncover the mysteries of matter, energy, and the very fabric of existence, taking us one step closer to answering the age-old question of where we come from and where we are headed. But the story of cosmic explosions does not end here. It is an ongoing saga written across the vastness of space, in the distant light of dying stars, in the collisions of galaxies, and even in the quiet potential of our sun's eventual fate. Each explosion we have explored today is a testament to the incredible scale and complexity of the universe, showcasing its capacity for both destruction and renewal. As we pull back from these cosmic events, it is clear that they hold more than just scientific significance. They inspire wonder, curiosity, and a deeper connection to the universe we call home. Now, we would love to hear from you. Which of these cosmic explosions captivated your imagination the most? Is it the enigmatic gamma-ray bursts, the saga of Betelgeuse's eventual supernova, or the incredible prospect of galaxy cluster collisions? Let us know in the comments below, and if you enjoyed this journey through the cosmos, make sure to like this video, share it with fellow space enthusiasts, and subscribe to our channel for more incredible explorations of the universe. Remember to hit the notification bell so you never miss an opportunity to journey with us into the mysteries of space. Thank you for watching, and until next time, keep looking up at the stars. They have so many stories to tell.